Given that the momentum in the gas expelled by a rocket's engine expressed by delta P sub gas is equal to V sub E delta M, that's the exhaust velocity times the certain amount of gas has been expelled, equals the momentum gained by the accelerating rocket expressed by delta P for the rocket is equal to capital M, which is the mass of the rocket, times acceleration times delta T. What is an expression for the thrust force on the rocket? So kind of the way we're thinking about this is like in a time delta T, an amount of fuel corresponding to delta M is expelled as exhaust. And we're suggesting that the amount of momentum gain of the rocket is equal to the amount of momentum put into the gas. Really, though, those momenta are in the opposite direction, but this is kind of like recoil, right? This is kind of like when the donkey and the ogre were talking about getting shot out of a cannon. You can have a system that starts with zero initial momentum and then winds up with one part of it having momentum to the right, the other part momentum to the left. So, in that sense, if I think of this rocket as gaining momentum to the right as a result of it pushing out or expelling momentum that is directed to the left, then that can explain how it accelerates by a rocket engine. And this is maybe not exactly looking like momentum conservation, but I'm just saying, hey, set those two momentum equal to each other. In other words, the V E delta M is equal to, and here I said momentum of the rocket, right? I didn't put rocket as a subscript before, but that is the same expression we had earlier, so that's what we're talking about, right? Um, so we're putting in this MA delta T for that. And it's asking us to find an expression for the thrust force on the rocket. Now, this is a formal example, so I think when we trigger the slide here, it's going to show us the answer to that. But I feel like we could probably do it without having to look at that, because I'm looking at this and I'm thinking like, well, what if I divide by delta T, right? Because I kind of remember what the key concepts page had. And I remember there was a delta M over delta T in there somewhere, right? Actually, I think it was kind of like what I'm writing right now is what it was, right? And that is equal to MA. Oh, we've seen MA before, right? That's Newton's second law. So maybe if our model for this rocket is here it's accelerating, and if I put in a free body diagram here and I just say, hey, this is the thrust force, right? I'll just put F sub TH. Then Newton's second law, F is equal to ma, would turn into that singular thrust force is equal to the rocket's total mass times its acceleration. But comparing that to the formula we just got, it's pretty clear that it's the same on the right. So maybe this thing on the left really is the expression for the thrust force. In other words, I think the thrust force is equal to this exhaust velocity times delta M over delta T. Now, you might recall on the key concepts page, I did have like an absolute value there, so I don't know if I can argue how that came out here. Maybe the slide will say something, maybe not. But it does, I think it does kind of the same thing right here. Just it gets this result that we just had, and then it says just this suggests that the thrust is that with absolute value signs thrown in, since delta M over delta T is in a, it says formally negative, but I think what that really means is like if you're defining it mathematically, it's very likely to be a negative because you're burning up mass, which means it's a negative rate. You know, if I don't know if that makes sense, right? But it's like if you're gaining in something, it's a positive rate. If you're losing something, it's a negative rate, which if it's your bank account is generally bad, right? But if it's rocket fuel burning up, that's just what naturally. Wouldn't it be cool if you could have a rocket engine, right, that created rocket fuel as it? That sounds impossible, but anyways, but that's what happens. So we need to have those absolute values, and it says there are different conventions possible for the signs on other variables. So definitely some, you know, if you look this up in different sources, you'll find some different notations out there. I've kind of simplified the way that we got to this compared to what you will see if you go and look up a really mathematically correct derivation. It has the potential to become quite a bit more complicated than what you've seen here, because I kind of simplified things by just looking at two momentum changes and saying them equal to each other. And kind of my tacit assumption there was that we're thinking about a system that started with zero momentum. Well, that's really only true maybe when the rocket is sitting on the pad before it's launched, right? So in that sense, to do it correctly, you maybe have to account for things like that a little bit more carefully.